Welcome everybody. My name is Kevin Clements, and I'm here today to talk to you a little bit about optimization techniques. This would focus on big data. Now, when we say big data, that could be something as simple as big data running on SQL. How would we deal with essentially the database structures there and make them faster and more performant? But it would also entail working with something like Hadoop or even Spark today, which are more prevalent when it comes to large data sets and disparate data sets in particular. So we're going to talk about a few systems out there, and we're going to look at, of course, defining the ways in which we can make this better. So the overview here starts out with the idea of optimization. And optimization can come in many forms, typically within organizations. When we start to process large amounts of data, we need to think about the structure of that data. And in particular, as I said, we'll talk about both on-prem and cloud solutions. So the methodologies that we're going to look at and focus on sort of cover off here in 5 areas. We start with standardizing our collections and formats. So that's the data formats, things like that we want to be very aware of as we move through and utilize our optimization techniques. From there, we'll look at tuning algorithms, and we can talk about the different types of algorithms and where you might gather those today. We'll look at AWS momentarily and talk about a few things around that. We'll improve the data quality integrity. This is a very big part of what we call data governance today and master data management. Most organizations have awareness of data governance and master data management, but very few actually apply it properly so that the data engineer or the data scientist can take advantage of that with those large disparate data sets. We'll look at latency and how we can get around that, especially around real-time data today. And then finally, leveraging some of the latest technology. We'll talk about
Kevin.
Throughout. So,
Alex. Sorry to interrupt.
Yeah, go ahead, Alex. Yeah.
Sorry, I think you haven't started the broadcast. I just joined. It says attendee still on hold. Start broadcast. Did you hit start broadcast?
Yeah, there's nothing on my screen for that.
Doesn't show start broadcast. Oh,
No.
sorry. Maybe my screen is doing something weird. I'm gonna just click start broadcast. Can you check that this people is listening to you before? Sorry to join late. Okay, let me click start broadcast.
Yeah, everything is showing on mine okay, and it is showing that I'm broadcasting.
Yeah.
Is anybody not seeing the information?
Yeah, something my screen didn't show. Sorry to interrupt. Sorry.
Yeah, no problem. Thanks, Alex, for checking in, though. I mean, that's important because I do want to make sure that everybody is okay. Yeah, so they're telling you they can see it. Thanks, folks. It's always good to check in with that. So leveraging the latest technologies, we'll look at different technologies in use today for working with big data sets. I mentioned the idea of master data management, and as I said, this is sort of a policy that goes into play within an organization. It's part of a term that you'll hear as data governance, and data governance, there's strategies and frameworks and so on. Really, it's about the collection of all of the information in the organization and understanding of where it is, and the understanding of whose responsibility it is within the organization. It could be the responsibility of a single individual, often, in a larger organization, the CTO, even the CIO may have that responsibility. In other organizations, it's organized a little bit different, just because in some cases, and I hate to use this term, we end up with siloed units, business units in particular. The idea of master data management goes hand in hand with having good data governance. And data governance just identifies all of the data throughout the organization. It identifies who's responsible for it, and what I like to call the who, what, when, where, why, and how. Who collected it? When was it collected? Why was it collected? What data and data sets, either does it work with or did it derive from? This is an important piece for changing data in the data lifecycle. And then how, right? What methodology was used essentially to collect it? Often the why is something to do with policy. It might be something to do with regulatory policies, like governmental policies, like Sarbanes-Oxley, things like that. Might be other reasons. Master data management, and there's a lot of tools for this. Informatica has an MDM tool. IBM has an MDM tool. Talend has an MDM tool. There's lots of organizations out there that can provide you tools. But the overall part that we want to take away here is that we are looking at what we call a single truth. So we have a single master record for each person, place, or thing in the business. And as I said, that's the single truth. We don't want to have, the customer phoning the sales department taking down information, and then passing that information to the order department, or invoicing or shipping. And then the next time around, the customer comes in and says, oh, I've got an update to my information. And so the salesperson writes it down again, passes the ID of the user along this time instead of the rest of the changed information. And of course, the databases that are now siloed in those other parts of the organization are not in sync, and perhaps the item gets shipped to the wrong location. So having a central repository or a central truth, that's really the idea behind master data management. It is an important concept around optimization, because without this, we end up having issues in understanding where data is within the organization. Here, meta or reference data, that's the information of the who, what, when, where, why, and how. It's going to change over time as the data lifecycle continues throughout the organization. Some organizations have very large amounts of data. My organization, we work with about 35 exabytes of data in the cloud. In doing that, we definitely have to have some kind of management of that, or it would be a nightmare to know where the data is at any time in the organization. So master data management, put that on your checklist, because it is important to understand, and organizations should be using that. A lot of this comes down to optimizing the data in some way. Now, we talked about quality, things like that. When we look at quality, we're often looking at the data engineer being involved in essentially the ETL process. So extracting the data, transforming it in some way, and that might be cleansing it, validating it. There's all kinds of other reconciliations that are done with data through that process by the data engineer. The idea here is that as we get larger and larger data sets, and as they become more complex, they also are prone to more errors. And sometimes that's introduced by either the data engineer and the data scientist. And we have to go back to this concept of bias, and we have to go back to the concept of the transformation of the data, which could skew it in some way. And by that, I mean, maybe we're filling in values that are missing, not a number, those kinds of things. And we start to fill it in with maybe the nearest value, or maybe we use a median or a mean. At some point, the data gets skewed. Now, there's a little bit of a side to this. As long as we know that the data is skewed, that's okay, because again, from that perspective, then whoever you're presenting the data to, the stakeholder that asked for it, will understand that there was some kind of skew involved in the data in order to fix it or reconcile it. But we need to say that up front. The other problem that we get into is kind of the joke down at the bottom, being a Canadian, here's Michael Bublé. Anyway, you can see that inconsistencies can appear in other ways as well. We mentioned about customer address just a moment ago, when we said that the different silos of the data store may have different addresses connected to the user at any one time. But here you can see another example where we get into the issue of how was the record stored in the first place. So is the full name? Is it an initial name? Is it, the abbreviated name that he goes by, to friends? This is something that, we need to work on, because this will present, again, inaccurate information throughout the database. We would now have 3 entities, possibly with the same information that would need to be reconciled, as I mentioned earlier. Standardizing data, by far, will lead to good data quality. It's not the only way of doing that. And we need to understand within the organization the data quality itself. Believe it or not, oh, that's really hard to see. It's because it's a link. Let me go back and put blue on that so you can actually see it. What it says there is MIT Sloan did a study recently around bad data, and they found that 15 to 25% of total revenue within the organization can be affected by keeping bad data over a long period of time. You're making decisions on essentially that flawed data, and that can have a detrimental impact to the organization. Oh, and by the way, my handout is available to you. It's there as a link in the handout section. I can also make it available from a URL. So let me do that while I think about it, because otherwise I'm going to forget. And I do want you to have a copy of this. So I will put that in the chat as well. All right, there you go. There's the link in the chat for the file. Okay, so we talked about data quality. We talked about kind of the integrity of data, standardizing data. How do we go about that, right? How do we go about that? Well, we said earlier about the ETL, or sometimes now known as the ELT process, depending on the types of data sources that we're working with. ELT in this case would refer to working with queued environments like RabbitMQ or Apache Kafka, where there's a middleman. You produce some kind of output. The middleman, being Kafka, a broker essentially, works with your data. Here we can modify the data, taking time windows, time slicing, modifying it, by adding in essentially a data frame that we can then query against in SQL on that broker, and then provide that output to different types of consumers. The consumers may do further work with that to ETL, or extract, transform, and load it after the fact, but there's that middleman kind of sitting there and working. So we often see this being done with tools like Apache Kafka, as I mentioned, or RabbitMQ. There are others. My organization, we use something called Redis, Redistributed Information System, and it is an in-memory data store. We also use Spark with Spark Streaming as a basis for this. And again, Spark Streaming works with data frames, essentially tables in memory that you can modify and query against. This will help in removing or replacing anomalies. It will make sure that we can enrich the data as required, because we can take the columns that we want and leave out the other ones. But essentially, it gives us a way of creating that data pipeline that is so critical today in the movement of data itself. So tracking, tracing, right, the audit process, and of course, as we said, with the life cycle, we've got that data lineage that's available. Speaking of actively working with the data, there are lots of tools again for this. I mentioned MDM tools a few minutes ago. There's EDC tools and others that we'll talk about and actually look at here shortly. So finally here, increase, really what we're trying to do is add in additional facts, and this is really what this is, facts about the data. Now, I have to be careful with that term, because some of you may know that term as features, which is additional columns. Some of you may know it as facts, which tend to be numeric values and things like that. So I'm going to use both terms here. You may also hear the term dimension, which is quite often used in, if I spell it right, which is often used, I think it's a DI, isn't it? Yeah. Which is often used to provide column names or additional information. So that's really what we're talking about here, augmenting the data in some way so that we understand it. So who touched it, that doesn't really matter. We can audit that. But who made changes to the data, that's where we want to have that reference data so that we know, what has changed. You'll notice here it talks about relevance, searchability, accessibility. This one in particular is interesting today because we have so many tools around that based on things that were developed at Google. You've got Elasticsearch, which can help for searching data. This is assuming that we have some kind of either relational or non-relational database, maybe MongoDB, maybe an Oracle database or an MS SQL database. We can apply these search capabilities, indexing essentially, outside of the data store. As you may know, when you start doing inserts and updates and deletes, this affects, of course, the indexing of the system and can slow it down, whether it is a NoSQL database or an SQL database. So the idea is to move that outside of the data store and use some kind of third-party tool. Both of these are open source. We could also use Lucene, which is another product for this. They would be all compatible with being able to create searchability around that, linkability, and of course, the big one at the end, especially for organizations today, involves compliance. So we have to think about, is this a HIPAA or FedRAMP or FIPS or, Sarbanes-Oxley? What compliance do I have to be in here? And again, that goes back to our auditing capabilities that we mentioned before. Reliable data is important. As I said earlier, the last little bullet there, talking about poor decisions made on, bad data. This is pretty common today. So there's this last one, data integrity. Again, we're trying to determine the consistency of the data here. Lots of smart data processing can be done today. Think about form validation. If we're collecting things from the web, we can use JavaScript and other technologies today to do form validation, make sure that the user is actually putting in the right information. My mom was a data entry clerk in the 80s, and it was very important to get things right as they were typing it in, but it still led to often mistakes. So here, we can augment what the user is telling us by certainly using these kinds of techniques. Access controls, of course, that leads to ensuring that the data is protected. We mentioned auditing earlier, different types of auditing tools. If we are in the cloud, most of those tools are available, like CloudTrail with AWS, Azure, of course, with the IAM, and Google with the IAM features allow us to essentially audit who's touching the data and when. Penetration testing, of course, we need to be very, very careful about who has access and how they can get access to it. We certainly don't want to be fined, $750 million like Entrust was recently, not Entrust, Equifax, pardon me, was fined recently for not fixing something like a Log4j issue, which led to about 150 million pieces of data being available out there in the cloud. All of these things, plus achieving data quality, will ensure that the data itself is fit for our processing, whatever that may be, machine learning, AI, just simple queries, for that matter, doing some kind of record set or result set for our standard SQL or non-SQL databases. All right, the next thing that we're going to talk about is latency, and this is an important piece today. We have all kinds of tools to be able to work with. For instance, this is a Hive data store connection where I'm connecting to Hadoop. And you can see here in the window, we have some databases, and I've actually gone on to use the one called wasadmin DB that I obviously created earlier. Standardized queries, that we would normally do on the data store, but that's going to be the first place that we're going to start. So, assuming that we have some kind of data store in there, what we can do, of course, is start to work with the data. So maybe we do a count of the data. Assuming that there is a billings table, then selecting the count of that should bring back information for us. However, the processing of that, just to do a simple count, as you can see here, is taking a considerable amount of time. The reason for that is that Hadoop on its own with Hive is not very efficient. It has to essentially plan, like we do in SQL with the optimizer, the path in which it can go to get that data. In the case of Hadoop, it now requires us to use some kind of mapping and reducing, parallel processing, to work with the data. And you can see just a simple count. We only have 100,000 records in that billing table. But the time that it took was about 45 seconds. Now, supposedly, right, I can go back into that, and the more I run it, because of the fact that it loads up some of that data in cache and elsewhere, would improve the performance of the system. Another way to improve performance would be to set the particular type of engine that I want to use. Sometimes when I paste it, it doesn't copy everything. So let me just go back and say set. So in Hive, we can set the particular type. See, it was there. It just didn't like my query. We can set the particular type of engine that we want to use. Initially, when we work with Hadoop and Hive together doing our queries, like the select query that you saw a moment ago, Hive supports SQL-like queries used against a non-relational database, in this case Hadoop, distributed. We can set the types of engines. By default, the engine is HR, what we call HR, or typically map reduce. Okay, so map reduce, meaning parallel processing. Parallel processing with MapReduce is efficient, but not as efficient as using other techniques. So today, when you're using something like HDP, this is the Hortonworks data platform, then maybe what we need to do is try different engines depending on the type of data we're working with. You'll notice in this case, instead of being set to HR or MapReduce, we are set to TES. TES is a faster engine for data services on Hadoop, but it's not the fastest. We could go somewhere else here. The next choice above that, which is still experimental today, involves using Spark, an in-memory data store, for part of this engine, which will improve, of course, the performance. Instead of having to do a lot of file I/O, the idea of using the data store in memory, right, will speed up performance because it's already there in memory. Whereas SQL and other types of data stores often have to move data from an on-prem environment where you are storing that on disk, hopefully not magnetic anymore, but a lot of organizations still have magnetic disks. We want to move that to probably an SSD drive or some kind of RAID drive and take advantage of the performance that they offer for our applications. That's just one way of doing it. So from an optimization point, right, we can come in and we know that there's going to be some latency in the data. If there's going to be latency, one aspect would be to set the engine to a different type. Okay, perfect. We've set the engine to a different type. We go on and we still notice that it takes some time for that application to really get the data that we're looking for. This is not unusual. Again, when we look at systems today, it's pretty common to encounter large data sets where that can take a good deal of time, to return information. For instance, if I was to run something like this query, which is going to be selecting the sum of the data. The little tool here is fun. There we go. Rather than me type them in. We're doing a sum function, so we're doing an aggregation. Again, we need mapping and reducing. You'll notice that only one mapper is being used here, and that's because I'm on a standalone instance of Hadoop. That would be wonderful for doing testing on, but as far as being performant, not very performant. We're going to get a lot of latency going on here. So the idea would be to have more than one node. Splitting that data up in some way would allow us to essentially have that data processed and then returned. All right, so this one was a little bit faster. I think the first foray up above to do the mapping and reduce. So the map phase was about 14 seconds. And then to do the reduce phase here was about 5. Mapping is just basically checking for all of the keys in the table, essentially, seeing if there's any duplicate keys. If there are duplicate keys, it will count those. The reducer is more like a group by. So it kind of does a grouping of all of the results. Two things for doing performance faster here. Setting the number of mappers that we want to use, and we can do that directly in the command line by setting those values in Hive, as well as setting the amount of reducers. Now, for a properly organized, organization that's doing this a lot, you're probably not going to be running these commands by hand. Most times these commands will be part of a larger set of queries that are most likely written in some kind of programming language, like Java and so on. In doing that, working with the Java instances and so on, we also have the ability within the code to make modifications. So from that perspective, it's quite common to see folks modify or change that data in some way by on the fly making changes to the actual data set itself. So we see that quite common there for programming, at least. So there's kind of two ways of improving, Hadoop here. The third way would be to go back to some of the actual 1,600 items that we can set within the Hadoop environment. This is the Hadoop documentation, by the way. And this is looking at the core values that are set within the Hadoop documentation. From this point of view, in a language like Java, you have the capabilities of working with the individual named values here and setting those values to some value larger or smaller, depending on the requirement of your operation. So for instance, you might want to change the idle timeout, that is set here to 60 seconds to some other value. You might want to change the caching to some other value. All of these things can affect the performance of Hive and other tools that we might use on top of Hadoop. However, I want you to be cautious about this. Unless you are the Hadoop administrator, don't try to get down at this level in the data store. Rely on tools like Java, where other tools out there, Python and so on, will interconnect as well. And with those tools, we can set automatic settings here, which will help us be more performant. Okay, but from the administration point of view, again, higher level aspect here, this would be another way of essentially getting over that processing latency that we have to worry about. Traditional storage models, right? as we said, they have to retrieve things via file IO. So whether it's a RAID system or whether it's a standard, NFS, the data is brought across the system itself. Today, really what we look at is distributing that data, taking advantage of parallel computing, and ensuring that we have some way of accessing the data. Partitioning the data, whether it's in SQL or other ways, is possible. So one of the first things that we do with SQL is we partition the data into smaller sets. For instance, the example I generally use is, months. Instead of working with a whole year of data, what we may decide to do is to break that data down in some way and slice it up. Often month is a good idea to do. Sometimes if it's global data, you would do it by country or maybe by region. These are simple ways of partitioning data. The same can apply here in Hadoop. So the next part of that then would be to look at perhaps partitioning the data in some way. However, that may not be helpful. And the reason that it may not be helpful is the format that we're using may not logically support this kind of operation. So we have to be, again, sort of aware of the format of the data that we're working with as we're doing this. You can see we've got data here on the left-hand side is text data. We start to compress it in some way. Typical compression would be RC files or Parquet files. For instance, AWS, Azure, and Google all use Parquet format for storing their data long-term, whether it's in the big table or an S3 bucket. This is a format that you should be aware of. And most languages have a very simple way of converting data from one format to another. Even down at the bottom there, you can see with Hive, we use something called an ORC file to work with this data. And you can see the difference in doing so. We get down to about 131 gigabytes of data from that original 585 gigs. So the third way really is to understand the data sets themselves, because once we understand the data sets, then we can take and put into practice ways of manipulating that data so that that data set is smaller to work with. That's probably going to mean that we need to do some kind of specific operation around the data to do the conversion. So we're not going to work now with the transactions data. If we did select count star from transactions, which would be a typical way of finding out how large the data set is, we're going to see that this one's got 1 million items in it. At that point, the data set is quite large, and it's taking up a large space, probably maybe in a single drive, maybe distributed depending on how we've partitioned it, but it's still going to be a lot of data to deal with there. It's almost a 1 million records. So the idea would be to convert that in some way. This is the way that we would do that. We would create a new transaction table, this one called transactions_orc, storing it as orc, but selecting it from our original transactions table. So that conversion of that to this new format is going to compress that data. By the way, it compresses it into binary format, which makes it that much easier to deal with, so that we don't have to deal with nefarious items. We can refer to everything in bytes and binary size. And this is going to give us, of course, an easier way to be able to work with the data source that we have. By the way, in my examples here in Hive, I have left the output on so that you can see actually what's going on here. This is something that you can actually turn off in the real world, and you would just get your return value after a certain time. But for the purposes here of what we're doing in class, I thought that it would be important to see it here in the seminar. Again, it's created the table, and now we could go ahead and take a look at the table itself. So we're going to describe the table. You'll notice when we start to describe the table, there's a lot of information that is here, who has access to it, the owner, when it was created, things like this, which are pretty common to our data sets. And then when we start to look at the formatting and so on, that's when it becomes important. And you can see here that it actually gives us the full location of where this is on the file system in Hadoop. It tells us, of course, the database. It tells us when, and who has access to it. All of those things are important pieces for us going forward. Notice that this database is a transactional database. So even though we are using essentially a distributed file system on Hadoop, we are still able to have transactions, ACID compliant transactions done here in this environment. And then of course, down here, the input formats are listed as ORC, right? So the import and output format for that. So stored as an ORC file. We can do other things as well that would allow us to have better performant queries. The next one here is pretty common today. It's something that we often do in SQL as well, and that is to create a materialized view. So a view, again, organizes the structure of our file, but doesn't actually call the data. It's kind of like a lazy loading scenario, where until I actually do my select against this, I would not see that. So again, just to show you another way of doing this, we can go ahead and start to work with a materialized view. Notice the number of mappers and reducers increased, and that's because we're dealing with different data sets in that query. I'm joining two tables. Essentially, I'm selecting the information from the ORC file, plus I'm grouping information here in the query, essentially here. The idea is that in doing so, I produce something that I can then work with directly. And again, like partitioning, materialized views and working with the different types of formatting will help the performance of our system. So will help us with latency. There's one other way that we can get around that and really get good performance from a system, and it's actually called bucketing. And bucketing in Hadoop is the idea of breaking up that partition data, even smaller sets. And so I should do a select against that just so that you can see the result here. Always want to show those kinds of things. So we'll get the first 10 rows back from our materialized view called invoices here. There it goes. Yeah, so you can see that sped up the performance of returning information because we've already preset that sum value. The time there has gone down considerably from, again, what we had a few moments ago. I think the sum took like 22 seconds or something like that in total when we were doing it. So as I said, the last type that we would look at often is bucketing. And bucketing in itself is a way of breaking up that partition data even further so that we have organized data in a particular way. There's advantages, there's some disadvantages as well. So, to be perfectly honest, you can certainly read information about it. This is a good article around that. So, why should we bucket? Why shouldn't we bucket? What does it do for us? This is the idea of breaking things down by year and so on. And then, of course, what we would do is further break that down into buckets. So you can see methodology here is to have smaller sets. For those of you that know anything about indexing, this would be very similar to indexing a file system, because of the fact that the actual process here is providing us with the ability to go to a certain part of the data set and then do our queries against that and only that part of the data set. So if we have 1 million or 1 billion rows, narrowing it down into buckets may mean that we only need to search through, let's say, 14 million records as opposed to 40 or 50 million records in our large data sets. Again, that's that performance that we're going to pick up because of the methodologies that we're invoking here. So again, from a Hadoop perspective, we can do partitioning, we can do bucketing, we can change the format of the data set and change the engine utilized. Each of those, wow, there's a typo. Each of those would be individual things that we would try, and kind of a stepped process, right? We would try one thing, see if that helps with performance. We'd try another thing to help with that performance. And the other mechanism here is to use programming like Java libraries for configuring the Hadoop environment. Through each of those, we are essentially coming up with solutions to the issue that we have, which is latency, right? The latency in the data itself. Now, there's one other way to do that, and some of you I know are aware of that because you've been in classes with me before, and that is to use an in-memory storage model. And the most frequently used ones today are often in the cloud. Not to say that we have to go to cloud. We could certainly run Spark on our own system, and we often do, or we run a derivative of that, like Anaconda with PySpark. PySpark in itself, running with something like Pandas data frames, is great for a single application running on your laptop or running on a desktop, but it's not very performant. And the reason is that it doesn't take advantage of really high-level parallel processing, which we can get from distributed systems like Databricks here, one of the inventors of Spark. The reason is that as we go to something like this, we can set up our clusters, our clustered environment. And now this example uses the community cloud, which is kind of like using Python and PySpark because it gives us a single cluster to work with. However, if you went to a paid version of Databricks, whether the data is in AWS or Azure or on-prem or in Google, you could interconnect with that and set up clusters of environments that would spin up automatically, what we call serverless or no ops technology that would be used there. Again, creating a cluster is fairly simple. You give the cluster a name, you pick the runtime environment version that you want to work with. You set the values for the instance. As I said, the free version is 15 gigs of memory. That's still a considerable amount of memory. You pick the availability zone. This one, as I mentioned a moment ago, this is the AWS one by default. And we could even set up our Spark criteria for working with our, in this case, Jupyter Notebook. And again, the notebooks are here for us to utilize. Earlier, one of the things I talked about was repairing data. So there's an example of doing that. And again, we might do something like drop columns or we might replace things to clean it up. The idea behind this really is to take advantage of the in-memory settings for that database. And the comparisons behind this, this is about 10% faster than working with SQL. And Spark in itself, I shouldn't have done that. Spark in itself is about 100 times faster than SQL. As long as it's configured properly, partitioning is done, distributed computing is done, sharding is done. These are all terminologies that we would use. Sharding, the terminology that I mentioned a moment ago, is equivalent to bucketing in our environment of Hadoop. So we will see folks quite often use sharded examples here for moving the data. But remember, the data in this case is in memory. It's not on disk, which again gives us advantages for performance. We also have the ability to, through this system, ensure that the data has some kind of long-term life cycle, as we said earlier. So why use it, right? MapReduce speeds up large data, parallel against the data set. Again, programmatically, you can take advantage of different languages. There's our partitioning, sharding, bucketing that we mentioned for the different systems that you may want to use. Again, advantages, HiveQL, which allows somebody who's a novice to still use SQL. If they have that, then people within your organization are able to continue those skill sets that they've been working with forever, maybe in a relational database, and use them here. And we also mentioned that the engine types can be set. So again, here, setting it to Hadoop or Tez or Spark would be appropriate. Tuning the algorithms are, again, another way of working with big data, especially. We don't just leave our machine learning algorithm or our AI algorithm on its own and let it run forever. As the data changes, as the underlying machines change, then we need to be kind of proactive, fitting, of course, the data to the objectives and the goals of the organization. Today, a lot of platforms choose to use online environments. So for those organizations that have that, this is an example of AWS SageMaker, which is again the tool to do this. Here you would often set up a notebook, which would be similar to a Jupyter notebook. So I mentioned earlier about doing these notebooks within your own environment, maybe with Anaconda, installing that for Python, because Python tends to be the big set of tools used today for data science and somewhat engineering as well. We see the transfer of data and so on being done in this way. Automation, it's quite common. And here, setting up the notebook would allow me to then do queries similar to what we saw a moment ago in Databricks here. Again, remembering that these queries can be saved and rerun, and that's kind of what we were talking about with the idea of the life cycle of the data. We also now have a life cycle around our algorithms. So keeping the algorithms around, performing what we need to do based on the data that we're working with is pretty common. So here I've started my notebook, but I could start it. And then I would go down and start to work with algorithms. So here the algorithms within SageMaker, I can either create my own, or I can take advantage of algorithms that I can buy off the shelf today. Lots of organizations are making those algorithms available to me, which gives me at least a starting point. Some of them are free, so I might take advantage of the free one, see what it does, and then maybe tweak the particular algorithm for what I need to do. You'll see that there's about 112 of these currently available for the machine learning environment. We also have algorithms available from this marketplace for other things as well. For instance, if you go down here to Augmented AI, this is, again, another way that we can take advantage of that. We can do the same on, Azure ML. We can do the same thing with Google Dataproc, which is the Hadoop version. The equivalent on that on Azure would be HD Insight. The ML version would be Dataflow on Google, and here it's SageMaker for machine learning. Again, you need to be run on a properly designed platform. Once we start running here in AWS, since this is done in a serverless mode, we are using essentially platform as a service or software as a service levels, depending on whether we create our algorithm or not. Then they're going to maintain the servers behind the scenes for us. It's not up to us to do that, which of course gives us advantage, right? They'll tune to the best machine that is possible to use. Identifying and fixing errors, I kind of already talked about that. I talked about the formats. So typically inconsistent formatting, fix the data, make sure that it's accurate. And accuracy really goes back to that idea of integrity and data quality here. We talked about going through and fixing values that are missing, right? So eliminating unnecessary data, maybe doing calculations or not, depending on what needs to be done. This is really why we want to be careful, because the algorithm itself, if it's dealing with data that's not been properly organized, will present problematic issues to the data set. Real-time data, we mentioned about online systems like Apache Kafka, streaming Spark, those kinds of things. These are real tools today that can help with that. We're not saying take away, our transactional SQL servers. We still need those, but adding things like Spark and Kafka can help with that quality. Also, because we can then break up the data before it's actually transferred into our final destination, it means that we have more control over the information that we're storing. In my world, we deal with lighting controls. We don't put every second of the 300,000 messages that are going into the data store. We don't need to. We use a fine-grained control system like Redis to allow those values to be updated in memory, and then every so often go out and read those values and store the information in the data store. And that's simply because we're doing calculations for energy reporting, and we can have 10-minute or 15-minute slices there because it's all using sensors that are offset by either 10 minutes or 15 minutes for those records. Sensor comes on, the light goes on. Sensor goes off, light goes off, means nobody's in the room. So there is no energy being used at that point. So again, taking those calculations into consideration. It's a faster way of doing it. We could even move that up. One of the organizations that I work with out of Austin is doing about 3.7 million operations per second, transactions per second, and using Kafka successfully for that. So again, no data loss, right? That's the key there with things like that. So we mentioned about machine learning. So there's new methodologies out there for that. If you are coming from, of course, the Python world, a lot of organizations tend to use things like scikit-learn. There is, of course, other tools out there that can be used, but Scikit tends to be kind of the first fallback for organizations working with machine learning processes. And you can see that we can do things like classification, regression, and clustering. We can also do pre-processing of data. This is really important today. The pre-processing of data allows us to basically extract the features that make sense. And I mentioned that earlier. So if you want to know more about that, this is a great link for learning about feature extraction and why that's important when it comes to working with data. So tuning, right? Tuning the data. This is going to give us good insight essentially to the data itself and the organization of that data. It's certainly impossible to do proper machine learning without proper organization. All right, that's what I have for today. We've covered off a lot of information. So let me take a moment to see if there's any questions around the information that we shared. I know, from an hour perspective, it's not a lot of time to do a deep dive into things, but I hope that made sense to you as we were going through. Questions around any of the material that we had? I can save this and share it if you like. I often do that to make sure that people have the opportunity to work with it. Oh yeah, I have to save it first. Hang on. Let's call it something with my name on it, so it's different than the one I uploaded earlier. There we go. And I'll save that for you and upload it here in the chat with my notes. Feel free, if you have any questions going forward, to reach out either to myself or to WebAge. We're more than happy to share this information with you and provide an opportunity for you to understand about the data sets. So Doyle said, would you please elaborate a little bit on transactions as true for Hive? Yeah. So the way that you can do that in Hive is, of course, set your own column value for that between your data sets. So the initial data set may not have a key that is used for linking the two tables, but you can do that. If the data sets themselves have similar data that can be joined together, either with a material view or by joining the table sets, you can certainly do that. Or you could add a new column to become the key to be used. Again, from a transactional point of view, right, we're dealing with data in a different way. If we need to go fully transactional with a relational data store, we would probably move away from Hadoop to something like Cassandra or MongoDB. Those would be better choices for a fully ACID compliant NoSQL data store. But again, this is something that we certainly look at overall. I can find an article for you too. Folks that have been with me before know that I really love some sites out there that is interesting. One is Towards Data Science, that is my favorite site to go to. So if you are not aware of Towards Data Science, it's towardsdatascience.com. Lots of great information here that you can glean by searching for that information. Lots of great examples around data science and so on. Don't forget, there's lots of free resources as well. May not be as good, but for those of you, Corey said, hey, my company doesn't pay for a lot of training. Yeah, absolutely, I understand. Look, I'm going to give you some resources to look at because it's not always about paying for stuff, right? It's about finding good materials. A lot of people laugh when I say W3 schools, but W3 schools right now have put together some really good information around data analytics, and it's excellent. So whether you're just learning something like Excel, or whether you're learning how to work with Google Sheets, or maybe you're moving into statistics or something like that, or maybe you're moving up into something else, take a look at some of these resources. They're actually very, very good. If you've got some other resources like Udemy or Pluralsight, you could use those as well. But this is a great little tutorial, takes you through kind of learning this as a start. Cost to you. Take a look at that as a way to start out, Corey, to kind of fill in some of that information, perhaps. Did I put that in the chat? No, I put Towards Data Science in the chat. Let me put this in the chat too. And again, the cool thing about this is you can actually interact with the code. So you can actually go here and try it. This one will do a scatter plot, I think, yeah. So again, you can go in here and start to change the values and play with it. So it gives you kind of that real world experience. The other one I mentioned was Databricks. The community cloud on Databricks is also free. So you can set yourself up there. There's great little tutorials on Databricks for that. And again, as a starting point, right, for somebody, this is a great way to start off. You're going to need to know the terminology around Python and PySpark or Scala to be successful here. Oh yeah. So you want to use the open data sets, Corey? Is that what you're thinking? Yeah. So the open data sources, so open dot what is it? Open.canada.gc.ca, I believe. Yeah, there's lots of good data there. The other one I talk about often is data.gov out of the US. Use that one quite often as well for training purposes too. All right, that's all I have, folks, but thank you very much for attending today. I hope that I've given you some insight into ways in which you can start to improve the performance of your systems, and in particular around some of the tools out there today that are available for you to work with. Back in about half an hour, we're doing a session on ML ops next, machine learning operations. So again, thanks everybody. Nice to meet you all. Wish you the best.